Okay, laws of indices then. It's a good idea, because we use them a lot, as I said, in calculus in particular, to have these to hand. So I would suggest that in your notes you have a separate piece of paper, either at the back if you tend to use a book, or somewhere so you can put it in a folder, maybe in one of these plastic wallets, and then you could put it along with the rules of differential calculus when we come to it, and so on. So some of these rules that you refer to quite a lot, handy to keep separate. So what I want you to do is to write down these laws of indices, and then what we'll do is go through each of these separately, and I'll explain them. So I'll just pause this video for a second while you write them down. This first law of indices, x to the a multiplied by x to the b equals x to the power a plus b. These laws of indices only work if the base, and this is called the base, is the same in each number. So x is a number, we don't know what it is, but it's the same number in both cases. So if x was 3, for example, 3 raised to the power number, it could be any number a cubed, multiplied by the same base, that's got to be the same, but because a and b are different letters, they could be the same number, but they could also be different numbers. So it could be 3 cubed times 3 cubed, but it could be 3 cubed times 3 to the power 4. What it's saying is, if I've got the same base, I end up with a number with that base, but I just add the powers. 3 plus 4 is 7. So that's basically what the first law of indices is saying. And it's not difficult to see where it comes from, because 3 cubed means 3 lots of 3. 3 times 3 times 3. And 3 to the 4 means 3 times 3 times 3 times 3. So I've got 7 lots of 3, effectively, 3 to the power 7. So that's the first law of indices. Of course, these numbers could be negative, and they could be fractions, and we'll talk about the consequence of that in a little while. So another example might be 4 to the power minus 2 multiplied by 4 to the power 5 would be 4 to the power 3, because minus 2 plus 5 is 3. So it works with negative numbers as well as positive numbers, and it works with fractions. 4 to the power a half multiplied by 4 to the power a quarter is 4 to the 3 quarters. So we need to be able to add fractions to use these laws of indices, because surprisingly maybe, fractions are not uncommon as powers. So what you've learned about adding fractions and later on subtracting fractions will come in useful here. What about the second law of indices? X to the a divided by x to the b is equal to x to the a minus b. So in other words, so long as the base is the same again, these all work for the same base. So 5 to the power 6 divided by 5 to the power 3 will be 5 to the power 3. 6 minus 3 is 3. Subtract the powers. And again, it's not too difficult to see how that works. If I've got 5 to the power 6, that means 6 lots of 5s divided by 3 lots of 5s. And of course, if I do that, I can cancel. 5s goes into 5 once, top and bottom here, once, top and bottom there, and again, so I can replace 3 of the 5s on the top with 1s, and I'm effectively just left with 5 to the power 3. Okay? What about this example? 5 to the power 5 divided by 5 to the power 7 would be, that's a 5 supposed to be, and that's supposed to be a 7. Try again. Right, 5 to the minus 2. So you can get negative powers when you do a division like that. Those are probably the two key laws of indices. The others actually come from them. So those are the two main ones. What about the third law of indices, number 3? X to the a raised to another power b equals x to the a times b. So what that means is, for example, a base x raised to a power, say, 2, and then cubed. What that's saying is, I multiply the powers. 2 times 3 is 6. And if we look at an example, that's maybe quite clear where that comes from. What's 5 squared? 5 times 5. What does cubed of that mean? It means 5 times 5 times another lot of 5 times 5 times another lot of 5 times 5, which is in fact 5 to the 6. So that's where that comes from. So these rules, it's fairly straightforward where they come from often, but they're very useful to know. So that's 3 rules of indices that we use regularly to combine and simplify things. And then we come on to some interesting ones. The inverse. This is one that comes up a lot, particularly in calculus, this inverse function. So 1 over x to the a means the inverse of x to the a. Inverse of x to the a. What does the inverse mean? 1 over. So inverse 1 over. That's another way of saying 1 over something. 1 divided by something. I can rewrite 1 over x to the a as x to the minus a. The inverse becomes, the inverse here becomes a negative power. Okay? So what do I do to use this particular rule? If I've got 1 over something, I just rewrite it as x to the minus a. So for example, 1 over 5 cubed could be rewritten as 5 to the minus 3. And so on. And again, it's not that difficult to see where that comes from, because if you look back at the example we've already looked at to do with this negative power here, look, if we look at this example we just looked at here, what's another way of writing this one? If I look at this one, 5 of the 5s on the top are going to cancel with 5 of the 5s on the bottom, leaving just 2 on the bottom. So if we look at this example again in terms of what we've just been doing, so 5 to the 5 divided by 5 to the 7, if I separate it all out, all over 7 5s, 3, 4, 5, 6, 7 5s. Again, we can replace a 5 on the top and bottom with a 1. 5s into 5 goes once. 5s into 5s goes once, top and bottom, and so on. Incidentally, if you're cancelling like this, you might not always write the 1, but it is a 1. It's not 0. You're not getting rid of it altogether. You're just replacing it with a 1. And if you look at it, I'm left with 2 5s on the bottom and 1 on top. So this equals 1 over 5 squared. And from the law of indices, that's equal to 5 to the minus 2. So that's where it comes from. So that's the fourth law of indices. Oh, I put it in the wrong place. So the fifth law of indices, this one and the next, and the one we've just been looking at, by the way, probably, as we'll see, the most useful for calculus. This one I always find the most interesting one to look at. For example, the cube root of x squared. That's how we'd say that if I wrote it down. The cube root of x squared. So what we have here is a base, x, to some root. So that could be any number, the square root, the cube root, the fourth root, and so on. And this can be a power. So the fifth root of x cubed, the cube root of x squared, as we've got here as an example. So these, again, are any numbers we want. Could be negative. And how do we write it in terms of the laws of indices? This is saying is that we write it just as x to the a. What's a? It's the power inside the root. So in this case, it's 2, divided by the root, which is 3. So we rewrite it as x to the 2/3. That's where the fraction comes from. I said fractions are often in powers. That's why, because if you've got a root, fractions occur. Yeah. If I'm trying to remember which way round these numbers go in the fraction, there's a good way of trying to remember it. If I've got something like the fifth root of x, so this is an example, Stuart, of where the power of x is 1 in this case. No power above means 1, x to the power 1. Which number goes on top of the fraction, which number goes on the bottom of the fraction? Well, it's easy to remember it because roots always go under the ground for plants and things. So the root number, which is 5 in this case, always goes at the bottom of the fraction. So I'd rewrite that as x to the 5th. You might be interested in how this law is arrived at, okay? You remember how it works, but look at this for an explanation. The square root of 3. No, let's make the number easier. The square root of 4. Anybody know the answer to that? 2, right. The square root of 4 multiplied by the square root of 4 then must give 4. That's the definition of the square root. The square root of a number is a number which, if you multiply it by itself, gives that number, okay? X to the half is a number. We don't know what that number is, but if I multiply it by itself, what must the answer be? Well, x, in this example 4, but x, okay? If you think about the first law of indices, what does the first law of indices say? Add the powers. A half plus a half is 1, okay? If you compare these two, look, they are the same number, effectively. So in other words, a half must be the root, must represent the root. And that's how it works, okay? Cube root would be the same. The cube root is a number which, if I multiply it by itself 3 times, will give me the number. And a third plus a third plus a third is 1. So the cube root is represented by a third, the fourth root represented by a quarter, and so on, which is effectively what this law of indices is saying here. The root goes underneath. That's the fraction we're talking about. The 2 is on top because it's whatever that number is, x squared, so there's a 2 on top. Okay, so that's the fifth law of indices. Those are the 5 main laws of indices. Here is the last law of indices. Anything, x can be anything, anything a negative number, a fraction, pi, anything to the power 0 is 1. That's what that's saying. Anything to the power 0 is 1. And that sometimes is something that we use when we're simplifying things. I'll leave it as a little exercise for you if you'd like to have a go at to prove why that's the case. Think of what I did to prove the first law of indices and the second law of indices. How can we use that to prove that anything to the power 0 is 1? I'll leave that for you to do.